Yes, we can start. We're full, so we're very happy to have Alexander Milovanov from ENEA. Alexander is well known for his work on disordered media and stochastic transport. So you'll be talking about subquadratic nonlinearities and Chrome models. So please, thank you very much.
Okay, thank you, Guilherme. Thanks also to David for inviting me for this seminar. So I will speak today about Anderson problem, and especially about the nonlinear Anderson problem. So the work which I am going to present is my joint work with Alex Yeoman from the Technion. And this is a topic from which we are working roughly 12 years. So destruction of Anderson localization on nonlinear lattices. I will introduce a little bit the linear problem first, within 2 slides, and then I proceed with the nonlinear problem. So I will assume that roughly you are familiar with the linear problem and with what is Anderson localization. In condensed matter physics, it's absence of diffusion of waves in a disordered medium. So why this? Because structural inhomogeneities of medium would scatter components of the wave field. So the wave function will get scattered, will get destructive interference on multiple scattering paths. And if the disorder is strong enough, this destructive interferences will result in localization. So a wave cannot propagate across a random medium if the degree of disorder is strong. So this result is well established in 1D lattices, and it's same as in 2D. For 2D, you have roughly the same thing as in 1D. For 3D lattices, the situation is more intricate in the sense that there is a stronger condition on the degree of disorder. However, if the disorder goes above a certain critical strength in 3D, you still get a localized state. If it is below critical strength, then linear field will not get localized and will spread across a lattice. Now, today I will not speak about 3D, and all what I'm going to present is in 1D. So in 1D, you have actually a localization of linear wave with rather weak condition on what is disorder. So the problem in this form was posed first by Anderson, who were looking into localization of the electron wave function in semiconductors. And he basically suggested that when you put an electron into a disordered system, then under some condition the electron wave function gets localized and there is no transport, no diffusion. It's a quantum phenomenon. In order to understand this phenomenon, well, one first needs to look into what has come to be known as initial spreading problem. So when you excite a wave process in some point, say for instance, technologically you can do it with a laser beam, which comes to a certain point in a random lattice, and then you excite a wave function like a delta pulse, then of course it starts to spread, despite that it is so linear. And the spreading, which is called initial spreading, consists in the fact that all linear modes which have significant value at point 0, they get excited. But at some point, this initial spreading goes to saturation. And the result of this saturation is that you obtain an exponentially localized wave function, which localization length, which, well, in theory, you can show how this localization length depends on the degree of disorder and on Hoping matrix element. So important thing is that the localization is exponential. So when we speak about Anderson problem, we assume that it is strong localization. Strong localization means exponential localization. It contrasts to weak localization, for instance, it's going to be power. So it's all strong. So all this is, however, relatively well known. So I put here the pioneering paper by Anderson, who got his Nobel Prize in Physics in 1977. So ever since, this phenomenon has been quite studied, condensed matter physics and beyond that. I should stress that Anderson localization is a wave phenomenon, and moreover, it is a generic wave phenomenon. Generic wave phenomenon means that it applies to any kind of wave. And experimentally, in fact, Anderson localization was proven for the localization of electron wave function, for localization of light, for localization of matter waves, for localization of spin waves. So it's something that pertains to how a wave process is organized. I'm not sure if people have seen localization of plasma waves as well. Maybe yes, maybe not, I don't know. So with these premises, I go ahead and go for nonlinear. Well, maybe still about something about linear. How you describe localization in theory? Anderson proposed to write a Hamiltonian, which is now known as a tight binding approximation. So this is a specific form of Hamiltonian, which goes like this. You have this guy here, which is none other than Laplacian on a discrete lattice. Then V is a hopping matrix element, and epsilon n is something that emulates random lattice. So this is a set of random numbers which are taken, let's say, with equal probability from a unit energy interval and substituted here. So this is a random thing. And analytically, you show that this is well defined. So this type of Hamiltonian has a full basis. Then you can actually expand your wave function over full basis of eigenstates. And the eigenstates are all exponentially localized by Anderson. And they form a full basis in the sense that, well, you can basically introduce normalization condition, orthogonality condition, and as usual use this set of functions as your basis functions to solve any mathematically well-posed problem for Hamiltonian. Now you are trying to make things nonlinear. So what does it mean? You add this Hamiltonian, supplement this Hamiltonian with a nonlinear term. Then in the simplest form, you write just beta psi squared psi. So this is just a small, weak nonlinearity. And the questions are, so if you add this, what happens? Do you really continue to have localization also for the nonlinear field? If not, does it spread to infinitely long distances, or simply it spreads beyond a linearly localized state and then comes to saturation, or saturation never occurs and it spreads to infinity? If it spreads to infinity, which is the spreading law, and finally, if all this works for arbitrary beta or for some beta, and if there is a critical value of beta maybe, above which it spreads to long distances, below which it doesn't spread at all. So questions are many, and actually answers to these questions also scattered widely. There are many people looking into these problems, publishing, and the results of those publications were kind of controversial. So some people suggested that nonlinear field will not spread. It may spread to longer distance, but that comes to saturation. Others suggested, well, it will spread to infinity, and there is no threshold in beta. Others said, no. It will spread to infinity, but only if your beta is larger than a certain threshold. So why this controversy? Well, at first glance, you know, if you add this small nonlinearity, then it looks like that, well, you have a field which starts to spread. Psi n is a weak, a small function. You take it in a quadratic power, so of course it is very small. So if you add something small and to something that's localized, it is hard that you will get important effect out of it. But it's only at first glance, you know. If you look maybe widely on this problem, you can see that Anderson problem is essentially a problem of quantum localization of chaos. In this business, you look at nonlinear frequency shift. due to nonlinear term. And you also have normalization condition for wave function. And from this normalization, so if delta n is the number of states across which your nonlinear field is spread, then you normalize the wave function to delta n, you get that roughly psi squared is 1 over delta n. So your nonlinear frequency shift goes as beta over delta n. And then, if, however, your field is spread again across delta n number of states, then the number of modes that have excited is also inverse of delta n. So the relative effect of nonlinearity over the number of modes excited doesn't depend on width of field spreading. So if beta is large from the outset, then your Chirikov parameter is large, which means that you have chaos here, and then the relative effect of this chaos will not qualitatively depend on width of field distribution. So if it is there, it is there. It spreads. If it is chaotic for some reason at the initial stage, it will remain chaotic. If it can spread initially, it can spread up to infinity. And that was the main observation. So I think it was first Shpelansky to note that with quadratic nonlinearity in nonlinear Schrödinger equation, you get chaos, which, if it is there, it is there. It's preserved while spreading. So those observations, well, they date back to still to the years like 1993, I think, was a paper by Shpelansky. But the groundbreaking advance was this work by Pikovsky and Shpelansky in 2008. And they published a PRL where they suggested the following. So they said, okay, we have a linearly localized field. So if you add nonlinearity, then the spreading of the nonlinear field will be due to nonlinear coupling among the modes. Then, if you have many statistically large number of coupled modes, then the effect of their coupling will be some sort of noise process. And they suggested to consider it as a white noise. So if this is a white noise process, then the amplitude of the noise, so the modulus squared of the nonlinear term, is diffusion coefficient. So if there is diffusion coefficient, then this coupling term acts as to spread your field, so it starts to propagate. There is a diffusion flux due to this term, and they equated the diffusion flux to ddt of delta n squared. And on the other hand, because there is normalization for psi squared, which goes with a number of states as 1 over delta n, then these guys here, it behaves like 1 over delta n cubed. So Pikovsky suggested then that if you write d dt applied to delta n squared, so that is the rate of field spreading, and this is 1 over delta n cubed. So from this, by scaling, you basically obtain this scaling law. So delta n squared is time to power 2/5. And numerically, they showed that there is a seemingly a critical value of nonlinearity parameter above which they could see this thing. And that was their paper. So 2008 physical review letters. A funny thing about this paper that it contained only 2 equations. So one was the nonlinear Schrödinger equation, and the other equation is the scaling law. And then there were some numerical simulation. And it is turned out a little bit challenging now. So, well, if we believe in the theory of Pikovsky and Shpelansky, then, well, I knew about it from Sasha Yomin, and we were quite excited about that result, and we also wished to look deeper into it. Well, we had also a paper some time ago where we said, okay, if we consider a rather peculiar diffusion process with diffusion coefficient which depends on a range scale, then, well, we can write some sort of diffusion equation with d which depends on the number of states. Then it was funny to obtain its Green's function, derive. Well, we had a paper from 2014. It wasn't all about this equation, however, but never mind. We like this theory. There is only one problem, I think, about this theory, and this problem was noted already by Pekovsky and Shepelansky and the APRL. Simply, when they started to model this spreading, they found out that no, this 2/5 behavior is not reproduced in numerical model. So they had a rather accurate numerical simulation. So by running long the numerical model, they found that the exponent of the spreading law is actually smaller than roughly 0.4 2/5, and was more like 0.3 or something. And they noted in their PRL, and they said that, well, this is a challenge. We have a so simple theory which predicts a nice spreading law 2/5, where can be wrong? But simulations don't reproduce it. And they posed a question out to it. No, some people can say when there is a nice theory which doesn't comply with numerical simulation, then the versus for simulation, of course. Well, maybe. There was another paper, actually, by Flach, Kramer, and Skokas. And this group is very active and continues to be active now, especially Skokas is a very active guy. They ran their simulation for a similar problem. And they said, it looks like that the exponent here is 1/3, 1/3. So they say that no, there is no like 2/5 exponent, it's smaller. Now you ask me why we are making so much fuss about it. I mean, both behaviors are kind of sub-diffusive scaling laws. The exponents are numerically simple, so 0.3, 0.4, which is the difference? There is a difference. First of all, the time goes to infinity. So we are talking about the asymptotic spreading laws. So in the limit of long times, you of course wish to know the exact value. And also it's a nice theoretical question how to obtain the correct exponent, which is 0.3 or 0.4 or whatever, or different. So apparently people got excited about this deviation. And there was, in fact, a stream of publications starting from these works, which aimed to understand the exact scaling law and the exact theory which would produce the scaling law. And well, Sasha Yomin was one of those who got interested into it, and somehow he engaged me in this business, and we started to look together. Before I present my work, just the current way of thinking, how it is. I think there was a nice paper from 2018 by Sinyash, Manda, and Skokas, who basically said that there are two possibilities or two distinct scaling laws in nonlinear Anderson problem. So one is with exponent 1/3, and they associated with a regime which they called weak chaos, and the other exponent is 1/2, and they associated with the strong chaos.
Can you tell us what those words mean?
Oh.
I mean, like define what weak and strong mean as some parameter, large or small or something?
This was partly my work with Sasha, and I'm going to tell about it. But if I anticipate my answer, I have myself a great problem about saying what means weak chaos and what means strong chaos.
So tell us what you think it is.
I tell you, of course, this is my seminar. First of all, it appears I had myself a great problem about it. First of all, I believe that strong chaos should not be thought of as fully developed chaos. Like, well, in we have fully developed turbulence with Kolmogorov scaling law, where your turbulent eddies fill in densely the volume of a fluid. So something similar would be fully developed chaos when you have system of overlapping resonances which densely fill the imbined space. But still, it does not mean it's the same as strong chaos. Strong chaos simply means that the Chirikov parameter is large, but it does not tell you anything how these overlapping resonances are filled in the imbined space. So then strong chaos is less developed than fully developed chaos, but it might not be weak chaos in the sense that I'm going to define further.
I'm trying to get a simple answer. Is the criterion of strong and weak the size of the Chirikov parameter?
There are two ingredients. One is Chirikov parameter, so whether it is much larger than 1 or is of the order of 1 or much smaller than 1. But it's very rough parameter. You must know how your resonances are folded in the bind space, in the phase space. And then there is something coming with topology. So if you densely fill the bind space with resonances and k is much larger than 1, then it's fully developed chaos, but then this is a diffusion. And here we will never get into diffusion. You have subdiffusion, and there is a reason for subdiffusion, and reasons can be many. Or it is weak chaos in the sense of Zaslavsky, or because your resonances are folded in a fancy way into a bind space, so it goes maybe along rather complicated trajectories. Well, where it is stochastic, and you have large Chirikov parameter, but not everywhere. You may have domains of regular behavior, and the mixture actually of stochastic C and islands of regular dynamics. So whether that will be strong chaos, according to Monday, it is strong chaos. To me, it's something stronger than weak chaos, but it is not fully developed. So it's like a life. It's not like black and white. There are many colors to it. Now I tell you what we think is weak chaos, however, in this model. And let us do it quietly. So what we know? We know that there is a basis. So a full basis, we have a wave function, and we can expand it over a full basis, and we can substitute it into a nonlinear Schrödinger equation. Then there is a quadratic term, so if you expand, you know how to write the quadratic term. Then you have this guy from Psien. Then you multiply the both sides of this equation with phi and k star and sum over n, and use normalization condition with Kronecker symbol. And then you get your equations of motion for oscillators. So this is the usual oscillatory pattern. There is a coupling term, and there are coefficients. So it's hard. Now, this nonlinear term, if you look carefully onto it, it's just coupling among all AM1, AM2, AM3, and how many combinations you wish.
Can you speak up, please?
It's very hard to hear you, Alexander, particularly when you talk to the board.
Okay.
Many of us back here.
No, I cannot, however, speak loudly. It's my normal. I can only speak in your direction, but then I will not see what I show to you. So we just get this coupling term, which couples you all modes in this representation, because it is a very general thing. But then, talking to Sasha once, it happened, by the way, during a conference in 2009. Joseph Klafter and Ralph Metzler organized a conference in Italy, and they invited Chechkin, who was their collaborator. And Chechkin was collaborator of Sasha Yomin. And Sasha Yomin wrote to me that there is a conference, and he asked if I can come, and they were saying, no, I cannot come, I'm busy. But he insisted, and I came to my boss, and boss said, well, Sasha, you must go, because we pay you everything. So I went, I met Sasha, and we were sitting and discussing this problem, and suddenly just, well, I don't wish to repeat some stories from the Eagle Bar, but it's much simpler story anyway. It happened like we thought we have a solution. The solution was that let us take only next neighbor couplings to this nonlinear coupling term. If you do that, you can actually map your nonlinear equations for coupled oscillators onto a Cayley tree. And the idea is that this nonlinear term with self-interaction term you associate with a node on a Cayley tree, and each of these coupling amplitudes you associate with a branch of a Cayley tree, where you have one incoming and two outcoming nodes. And if the couplings are next neighbor-like, and you have an infinite sequence of these oscillators, you can put them all onto a Cayley graph. And the idea would be that each node on a graph represents a nonlinear oscillator. I don't see the red. Each node of the graph will represent an oscillator, and the nodes are representing the coupling nodes of the graph. So what it gives to you? It gives the idea why there is a threshold behavior in the system. Since you would say that a field propagates when the nodes are in chaotic state. Then you actually can say the probability for a node to be in a chaotic state, it should be something like Boltzmann's factor, which is exponential, where delta omega is divided by nonlinear frequency shift. And nonlinear frequency shift is your temperature of nonlinear interaction. Because you remember the relative effect of nonlinear frequency shift does not depend on the width of field distribution, then it appears that this guy here is nothing else than 1 over beta. So you say that the probability for an oscillator to be in a chaotic state is exponential of minus 1 over beta. So how it works? If you have a linear problem, so your beta is 0. So 1 over 0 is infinity, p is 0. That means that the probability to be in chaotic state is 0. All your oscillators are in regular state, and this blocks spreading. You don't have spreading then a nonlinear problem. That's fine. On the contrary, if beta is very large, then p is 1. So all nodes then are in chaotic state, and your lattice is transparent for spreading how long you wish. But then there is a critical probability, beta, or critical filling factor p, where for the first time you obtain a connected escape path to infinity. So you fill in with your chaotic motions a critical number of oscillators, critical number of nodes, but not all nodes, so as to obtain an escape path to infinity for the first time. This is a classic percolation problem, random percolation problem, which everyone knows how is solved on the Cayley tree. And for this problem, then there is an exact result. There is a critical percolation, there's critical probability when you get the percolation transition. It's 1/2 for Cayley tree with 3 nodes. In general, you write it as 1 over z minus 1, where z is the coordination number, and coordination number is the number of your nodes at each, the number of branches of the Cayley tree at each node. So you have 3 branches, and p is 1/2. Then you equate it to exponential of minus 1 over beta, make it 1/2, and you get beta 1 over logarithm 2. And this is a critical value. So you say that if beta is smaller than 1 over logarithm 2, you basically have nonlinear field, but which behaves as if it is a linear field. It cannot spread to infinity because it is subcritical. On the contrary, if beta is greater than 1 over log 2, you have enough chaotic states to permit escape of the wave field to infinity, and then you have transport. So the value, by the way, coincided roughly with up to 2 pi. We use 2 pi as 1 with the numerical result of Bykovsky and Shepelansky. And from this we obtain finally a spreading law, because we know how percolation transition on a Cayley tree occurs. We know the percolation transition, and we know the connectivity of the percolation cluster on Cayley tree. Then, if we do that, we write dispersion relation, and dispersion for random walks on a Cayley tree is just delta n squared as time to power 2 over 2 plus theta, and theta is connectivity index, and connectivity index is known for the Cayley trees, and it is 4. This is exact result in all this business. And you see you get 1/3 from this. So conclusion then, if you have next neighbor couplings only, then the escape of the wave field to infinity is thresholded. And the threshold condition corresponds to next neighbor coupling. If you have less than next neighbor coupling, then it is decoupled. You cannot escape to infinity. So this is the chaos, essentially. All all what is above this, above the percolation threshold, will correspond to something that one may call strong chaos, with that reservation that it is not still fully developed chaos. But anyway, there is a threshold behavior here, and the threshold behavior gives you 1/3 scaling. So that was our first paper with Sasha from 2012. Apparently, it got quite some level of citation. I mean, it seems that this model was fairly simple, and people understood the idea of percolation on a Cayley tree and why it gives the 1/3 scaling. So this is the first part of the story. Now, if you remember, again, this work by Manda and Skokos, they were saying that for weak chaos, they had 1/3, and for strong chaos, what they call strong chaos, they had 1/2. The question is how you get 1/2 then. No, you get 1/2 actually in a very simple way. First, we thought we should look into a quantum picture. I mean, look into quantum chaos. No, you know, when we say quantum chaos or classical chaos, it's all quantum in a sense. But when you say classical chaos, it's in a sense we use Gross-Pitayevsky equation and Milfield limit. So that would be classical, otherwise it's still quantum. But for quantum chaos, truly quantum, you basically have no reason to equate your noise source to ddt of delta n squared, since ddt of delta n squared assumes that you have some sort of diffusion process. We have no reason to assume this diffusion process. But what we can write in quantum chaos, that the rate of field spreading is given by Fermi's golden rule, that is by the rate of transition between states. So you equate it not to ddt of delta n squared, as Bukowski and Shepelansky did, but simply by Fermi's golden rule, ddt of delta n. And this gives you immediately 1/2. And this is what people see actually in numerical simulation. For quantum lattices, by the way, was work just devoted to spreading of nonlinear field in Hubbard model, and this gives 1/2 scaling for sufficiently large t. So it's for quantum. No, somehow we believed initially, and even wrote it on a paper, that for classical theory, in the sense of Gross-Pitayevsky, we still would have 2/5 as of Bukowski and Shepelansky. But now we believe that there is no such scaling 2/5. Simply we liked so much the work of Bukowski and Shepelansky and so much willing to get our own theory which generalizes their result, well, that we repeated, I think, simply their mistakes. In the sense when Sasha said that it's time to do our own mistakes, not to repeat mistakes from other people. So we produced a different paper, and now we believe that over half this result. It applies also for classical field for that simple reason that you have resonance interactions between modes. The resonant quantity ensures that you have the Fermi's golden rule. But still, well, you may be asking, we have this nice subdiffusion law, but why it is not diffusive? So again, what Patrick was saying, what is strong chaos and fully developed chaos? Why it is subdiffusion in the strong chaos regime? No, there are some ways to answer it. First, I show you some funny derivations. That suppose we have this law. So let me rewrite this equation with Fermi's golden rule and the rate of field spreading obtained from scaling of the noise term. So I have it here. Now I differentiate both sides of this equation over time. So ddt here, and then I differentiate on this part. I get minus a to delta n fourth ddt delta n, and ddt delta n I get from my equation, substitute, and then I rewrite the right-hand side in terms of a gradient, minus dtn over something. Then you see that this something is the inverse 6th power of delta n. And it is the attractive part of the Lennard-Jones potential, which you know from molecular physics. It is very nice. So you have attractive interaction between modes. So that is why you don't get your diffusion. You would have a diffusion process if there were no attractive interaction among modes, but you have attractive interaction among modes. Then which is the way to understand why there is this attractive interaction? There are two ways to say it. One, your spreading problem is actually leads you to non-ergodic behavior, because spreading is something inhomogeneous, and for sure you have mixture of domains of chaotic behavior and regular behavior. And regular behavior is an obstacle for chaos, so it squeezes your chaotic behavior into narrow regions, and then this squeezing is equivalent to some sort of attractive interaction between modes. It's one story. Another way is to remember that you might have, however, the temporal analog of a phase transition in this system. That is, you may get spontaneous synchronization of some modes. And this is a well-known result in theory of nonlinear oscillators. That is, if a spread of natural frequencies is broad enough, much broader than the coupling frequency, then your oscillators behave incoherently. But if the spread goes below a certain threshold, then some oscillators spontaneously lock into a synchronized state. So what you have actually a broad stochastic C, but within the C you just get domains where oscillators spontaneously synchronize, and they get from chaotic state into a regular state inside. And this gives you, again, this potential function, Lennard-Jones. So you have order, you have structure inside within your chaotic C. So you produce your chaos, but chaos becomes some sort of unstable, and it likes to produce structures from inside. So when we say that order is born from structure, order is born from chaos. Now, I can derive a kinetic equation for field spreading on account of this attractive interaction. And that is how, again, introduce a Boltzmann factor, which would y the potential energy due to Lennard-Jones interaction to temperature of stochastic C. That would be exactly the probability to quit a cluster after delta n step sizes on it. So it would, expanding the exponential function, would be 1 minus a squared 2t delta n. So this is large, so upon very large number of steps you get 1. Then there is then a probability to survive on the cluster after delta n steps, which is 1 minus p. So you have this nice thing. And then you might be willing to go from delta n to delta t, so to use a time lag. And then you get a distribution over delta t's, which is actually a waiting time distribution. So you have a situation in which you have clusters. Clusters capture waves, and there is a waiting time distribution to exit these clusters. This, by the way, was seen by Sasha Yom in a numerical simulation, the clustering and the exit time statistics. But if you have a waiting time statistics now, you just apply the classic scheme of continuous time random walk, which is just a generalization of Brownian random walk. So you put it on a lattice, you allow a particle to take a jump. Your jump, say, has a characteristic step size, but there is a waiting time distribution between consecutive steps of the motion. What you get out of it, you get a fractional generalization of the diffusion equation. You get a non-Markovian diffusion equation with Riemann-Liouville derivative over time, and the exponent of this derivative will be related with the exponent of the waiting time distribution. And we know from the exactly Lennard-Jones potential that this exponent is 3/2, because we get this distribution here. And then this alpha exponent will be 1/2. And from this you get essentially the delta n squared is t to power 1/2. That is what we see from simulation. So you do not have your diffusion process because you have interaction between modes, which introduce non-Markovianity, and the entire process goes with memory, and this makes it different from fully developed curves. So this is roughly about the quadratic model. Now, I have one part more to my talk. Just it will depend on how much you are bored now and how much time I have.
20 minutes.
Yeah. The problem with this part that it is quite mathematical. So my experience in presenting it, that it is really heavy to both to present and to conceive. So I just give you only the flavor. I will go a little bit fast and show you the problem and the way we solve it and the result, but not really going through mathematics. This problem concerns the problem of nonlinear Anderson model with subquadratic nonlinearity. So at some point, just we asked ourselves with Sasha, what if we, instead of putting a second power here, we write this 2s with exponent s being smaller than 1. It initially looked to us a rather academic problem, but in the end, why should we bother ourselves about its origin? We can formulate it in mathematical sense and then we look into it and we solve. Then it's another question from where it comes. On the other hand, once I think I was challenged by Patrick Diamond and later also by Guglielm, who was saying, no. You can put it as if you like, but please give us any explanation from where it comes. So I was challenged by that. I did not have a great answer at the time. Then the answer we proposed with Sasha that this is a compact form of nonlinear Schrödinger equation with distributed nonlinearity. So when you write it as a convolution with some kernel and the kernel of this power law form. In principle, it's just the discrete form of Riemann-Liouville integral, somehow a thing that appears in many applications interesting. Then in the limit of broad wave packet, you actually can go from this equation with distributed nonlinearity to this compact form. It's not, they're not equivalent, by the way. It's just one is an approximation of the other. Anyway, it looks like that it is good approximation. Why we are interested in this problem? Now just look at the Cherenkov parameter. There is a new physics coming with s being smaller than 1. And this physics says that Cherenkov parameter starts to depend on the number of states. So it goes with power 1 minus s. So as soon as s is 1, then Cherenkov parameter is beta. So as I was saying, you have chaos initially, then qualitative effect of chaos doesn't depend on spreading dynamics, so it is chaotic, it remains chaotic all the time. But here not. Here k grows with the number of states. So if your field somehow is such that at time 0 it is chaotic and it starts to spread, then the chaos enhances while spreading, and k is growing, so it becomes more and more chaotic and more prone to spread further. And this makes the difference. So we basically obtain then a spreading which is driven internally by something. Just anticipating our result, it results in Levy flights. So you don't have Levy flights in a quadratic model, but you are going to get them in this subquadratic model. Then, it's the result anyway. Before we arrive to this result, what we have to do some mathematics. So again, we expand the wave function over basis functions. Then it's problematic because if s is 1, you basically know what to do with this power. You immediately expand it. But if s is fractional, it's a mess. We don't know actually how to expand this function into a fractional power. So for this, we had to develop with Sasha a special mathematical procedure how to deal with it. And well, it took us actually 3 PREs to publish it in a final form. The idea is to use multinomial expansion and to propose something like iteration procedure. So to substitute this fractional power of a series by another series, which is built through an iteration procedure somehow up to infinity. It contains infinite number of terms. There is, as I'm saying, some heavy mathematics through which it would be a little bit messy to go. But the result of this calculation is actually very funny and transparent. And it contains in the following. So you can represent your fractional power s of that time, of that series, as graphically as a sequence of Cayley graphs. So in the first iteration, you have a Cayley graph, which very much likes what we had already in our quadratic problem for percolation transition. So it's a Cayley graph which contains three branches. It has zeta equal to 3. But there is one new element here, that the branches are disrupted, so they are represented by counter sets. And in a classical approximation, that means that the disrupted branches cannot conduct your field. So there will be localization. And we thought initially, we built the first iteration actually very fast with Sasha, and we thought that that would be the final answer to whole nonlinear Anderson problem with s smaller than 1, that if we don't have spreading for s smaller than 1 because of these disruptions, then basically we don't get spreading. And we even published it that for s smaller than 1, the field is, classical field is Anderson localized. Quantum not, because quantum field can tunnel here through disrupted nodes. But again, it appeared that we made the same mistake as people were doing when they were looking into psi squared, saying that quadratic nonlinearity is a small correction, so a small correction will not change stories. It changes, it does. So we need to look into a high order expansion of the iteration procedure. Then in second order, we then get again a Cayley graph, but the Cayley graph will have 5 nodes and not 3 nodes. And each of these nodes will be also disrupted. So again, at first glance, it looks like that them being disrupted prevent field from spreading to infinite distances. But here, not exactly. If you look carefully into the terms of the expansion, you find that there are some special terms in it. And special terms are those which come exactly with same fractional powers. And those terms represent identical wave processes. So them being identical means that you cannot distinguish between them. So instead of having actually 3 different, you can say that you have one just coupled. So it's strongly coupled state between 3 identical processes. So you glue them, if I use topological language. That is to say, you get degenerate state. And the degenerate state composed of 3 disrupted nodes produce your actually coupled state which can conduct a wave. And you had a funny thing that in the second order, due to the presence of degenerate state, you have single states which can conduct a wave process, and the field starts to be conducting in the next order. And you see this in every high order. Then in the third order, you build a Cayley graph with 7 nodes, of which 5 can produce a degenerate state, and the degenerate state will conduct, and so forth, and up to infinity, and you can prove it for any order. And finally, you say that because you identify your states, the presence of degenerate states is same as the presence of non-locality. They introduce some sort of non-local behavior because non-locality occurs from identifying their different wave processes, which you cannot distinguish. So all in all, it would appear that your system is equivalent to a nonlinear oscillator driven by a noise process with non-locality inside, that is by Levy white noise. And from this you can build transport equation, now not only with memory effect and clustering, which still remains there for the subquadratic problem, but also with Levy flights. And you have a very tricky nonlinear behavior in which non-Markovianity and waiting time statistics will compete with non-local properties due to Levy flights. Then you write essentially an equation with fractional derivatives over time and phase space coordinate, and obtain spreading laws, which you calculate as competition between non-Markovianity and non-locality. And this is seen from the exponents of those scaling laws, which would contain both the parameters of waiting time and jump length distribution for flights. And somehow it explains the simulations, what people see and how they perceive this type of behavior. So work is in progress. I mean, here I listed some of the papers we published with Sasha at different times, starting from our first paper from 2012. Somehow there had to be one more paper to it, just published very recently. But well, I wish to put all applications on one slide only, and I omitted this last thing. So roughly that is the moral of all this long story. So why Pekovsky and Shepelansky did not get the 2/5 behavior? Because the assumption of random phases, which they had, was wrong. You don't have random phases. You don't have random phases because you have resonant character of interactions. You have degenerate states which produce non-locality. You have synchronization of different oscillators. And in the end, you have nonlinearity, which means that you couple certain waves according to a resonance condition. And all this prevents you from saying that you have a noise process, which is a white noise. You have a source, a driving source, that's true. You have energy density due to this source, which is the modulus squared of the nonlinear term, that's true. But never to say that this is a white Gaussian noise. So there is no 2/5 scaling. So Cartagenum debendum esse, no 2/5 scaling. There is 1/3 for weak Gauss and scaling behaviors involving alpha and S for different regimes of not so weak chaos, not fully developed. Thank you for your attention.
So I have an infinity of questions, but we'll start with a few. It seems your story can be distilled to some extent to a message that random phases are not needed. I mean, and you know, Creighton made this point and infinitely long ago. I mean, I think in the 60s, early 60s, where he showed that the DIA propagator equation emerged as an exact solution of the random coupling model. You notice the randomness was in the coupling coefficient and not the phases, and there's a big difference there. So it begs the question, you have that at one limit, which I think is different from what you're doing, and then you have, as you say, Kuramoto at the other limit, where you have no randomness in the coupling coefficients. Can you pass smoothly from one to the other and recover both limits?
I'm not sure.
This would seem to be the relevant question here, right? You know the answer in the two extreme limits already. It's not clear to me you recover. I think you can recover Kuramoto. It's not clear to me you recover Creighton. And then the question is, to do something new, you have to pass from one limit to the other.
No, an answer I would give on the spot, unless I am willing to think more to it.
Another challenge for you.
Yes, you already challenged me time ago. Well, I believe that this type of subquadratic model, it just contains this alpha and S, which actually you can interpret differently. I mean, I showed you one interpretation for alpha, which used the Lennard-Jones potential, and then it gives you S in the end, because you know the overall scaling. There are different ways, actually, to approach it. So, under different assumptions, other assumptions, you may get a different estimate for alpha, and having same estimate for spreading law, you can get a different weight for Levy processes. So from this point of view, there is a ground to play. And alpha and S are parameters, well, which parameterize actually the various transport regimes here. From this point of view, I might assume there could be a way to interpolate between the different regimes. But whether these are really, if I think in terms of a phase diagram, if they are really not separate, the regimes, and you don't really have just clusters of different values not connected one to another, this I cannot say on the spot. It can be, however, different regimes for this.
It seems to me it depends on the PDF of the couplings, right? That's the central issue here.
Yes, how we think about coupling.
The other question I had, well, I mean, there's a third one, which is how you get, the hell do you get the exponents in a real problem? I mean, and that you know, Zaslavsky could get it for the accelerator modes in the standard map, of course, but I mean, that becomes, in real problems, is not so obvious. But let me go back to the toy problem here. You mentioned that you get a kind of Levy noise, okay? Well, going back to our friend Creighton again, as something that I think many of us could understand, you know, the whole point is the nonlinearity has both noise and a kind of nonlinear damping. And the interplay of these two is what defines a cascade process. So, I mean, why do you get noise alone? Why don't you get a kind of nonlinear damping piece as well here? Because then, I mean, then the propagation would emerge as a kind of cascading in your space, or which you could think of as an avalanche in your space.
No, that's right. That's right. To some extent, we are limited to our Hamiltonian model and the fact that we model it using the NLSE. But if we go beyond that, then you can be right.
Well, I mean, it would seem to me an interesting direction to bring some renormalization into the propagator.
It can, yes, it can identify to you the limit beyond the scaling law, and in the end work out as a boundary condition for the scaling.
On that topic, isn't it what you get when you consider the infinite sequence of odd Cayley trees? Because that's, you know, you have no percolation, then you have possibility for it.
Very nice words, Guillaume, but if you saw the formula, it wasn't there, sorry.
Please say again, you mean?
No, I'm just telling him to shut up. I think his answer is superficial.
Okay.
Other superficial questions? John?
Yes, let me yell so everybody can hear. On your first slide, you had the nonlinear Schrödinger equation with your h as the second order difference. Now in the continuum limit, you go to the nonlinear Schrödinger PDE, which, depending on the sign, I think, of beta, actually blows up in finite time if the energy is negative. Now, would you say that that's the equivalent of Anderson localization in the continuum limit?
No, that would assume the opposite side of beta. Right, we actually put it...
Yes, I think beta has to be positive.
Yeah, we say it is positive. Otherwise, you end up with all these dark solitons and stuff like that.
Okay.
Is that the self-focusing limit you're getting at, basically? Yeah.
No, you have the opposite. You have the spreading.
Beta, I assume, was positive here all the way. Yes. I mean, what happens? I mean, you could imagine you have a competition, right, between spreading and focusing. What happens if you had a distribution of betas? Have you thought about that? Different signs for different couplings?
Yes, yes, that's the work in progress with session. Maybe next time we have
a second question. I'm following you, Pat, with multiple questions. Pat's question about weak and strong chaos. I mean, in CFD people have these criteria in signals processing, like the flatness, the skewness, etc. And that tells you how strong your turbulence is and whether it's fully developed, whether it's intermittent, etc., etc. Now, why can't you do the same?
No, you know, I'm a little bit reluctant about term turbulence, since again, what means turbulence? It's something well defined in fluid science. When you have vortices, right, eddies. We don't have anything like that. We have a wave-like picture.
So in some sense, you have some resonance which cannot be incorporated in that usual turbulent picture.
exactly. And that's what destroys the random phase.
You can incorporate resonance into the picture.
I mean, not wave turbulence, I mean just hydra or turbulence.
Yeah, but I mean, you can construct theories for strong wave turbulence, right?
Okay, maybe. But
Well,
here
yes.
resonance plays a crucial role.
Yeah, well,
Yes, but I think the strong and weak here in the speakers thing isn't strong and weak. It's not weak turbulence in the sense of low Reynolds number.
Yes.
It's a question of is it spatiotemporal chaos, or is it really properly fully developed intermittency? That's the difference between weak and strong.
I thought his key parameter here was the Chirikov parameter, right? Which is basically the width of, in simple terms, the width of the island of resonance divided by the spacing, right? And he had three cases: strongly overlapping, marginally overlapping, and not overlapping. The other question I was going to ask, if you're marginally overlapping, it seems to me the addition of any other process becomes very critical in this story. Because if you have two islands that are touching each other, any residual collisions can kick you from one island to the other, right? And then there's a question of how meaningful is the definition of the model.
That's a good point. Somehow, it's a challenge in all this business, as I understood it, to predict really what people call asymptotic law. So what you obtain for infinitely large system and the limit of time going to infinity. So for asymptotic scaling law, you would actually use that kind of reasoning just for marginal coupling. How stable is it? It looks to be that, as you say, that marginal, small perturbances to it already violated, and you get very promptly into something like strong chaos when you have 1/2. At least based on numerical evidence, it looks like so. It's a rather elusive scaling law with 1/3. The way I imagine it, your field spreads, and when it goes to very long distances and long times, well, yes, there is something like t to power 1/3 there. But at any finite time and spatial scale already covered, you have residual spreading which goes like t to 1/2. And moreover, it appears that this 1/3 law, it works quite well for quadratic nonlinearity only, not for subquadratic. In subquadratic, you have only one scaling law which depends on s. So it's special. It's very special. But the quadratic nonlinearity is special.
Other questions? I think we've tortured you long enough.